My name is Bipin Thapamagar, and today I'm going to present about AWB-GCN, a graph convolutional neural network accelerator for with a runtime workload rebalancing. This is the reference for that. Okay, so CNNs and RNNs actually excel at processing images and audio and video, but they don't work well with graphs. So that's why special graph convolutional networks have emerged, which helps to learn information from a specific graphs. The thing with graphs is that they have a very high sparsity, so that's like above 99% in terms of graphs, so that they need some special hardware or special technique to optimize. Hardware accelerators for GCN is actually critical because of the large scale of the graphs as well as the large memory required and the optimization capability inside those networks. So what the paper does is it focuses on those optimizations so that the processing elements is heavily utilized and then the workflow or the workloads are managed and optimized at as well. So the main goal of the paper is to develop a hardware accelerators, which is AWB-GCN or auto-tuning workload balancing graph convolutional network. So it kind of is a efficient GCN interface that kind of addresses the workload imbalance problem. For this, it proposes three different auto-tuning techniques. The first one is distribution smoothing, remote switching, and evil row remapping, all done dynamically or in online during the running runtime. And then it kind of compares the performance and hardware utilization of their network with the other accelerators, other systems as well, using five different GCN datasets. So, a little bit about why this research is needed. So, traditionally, SCNN or sparse CNN accelerators are not suited well for the GraphNet neural networks because of the main difference of the graph data. So, graph data have a lot of sparsity. So, the nail graph, as seen here, has around 0.0073% of average density. So, that's pretty low. Whereas a typical CNN such as the AlexNet has around 27% average density. So that's why due to the low density, there needs to be some specific optimizations as well as if it's not optimized, then the size of the graphs will be very huge, which cannot be fit into the memory, so that could be a problem for that as well. So the other part is something called a power distribution. So what it basically tells us that graph networks are actually distributed into clusters of regions or cluster of rows. So in some rows, there might be a little bit very low data, while in some rows there will be uh, clustered of data, and there are special rows which have a huge density of data, which the authors define as evil rows. So there will be evil rows and regionally clustered rows as well, which you can see in the other figure as well. Okay. uh, The other part is with other GRN accelerators. So there have been some other GRN accelerators as well. So Kung et al. They condensed the sparse parameter matrix, but and then only took the significant parameters, but it kind of affected the accuracy. So Kim et al. They have designed a system where they develop a profiling of the workloads, but they only did that for the initial workload, which didn't work for the online or during the runtime. Hanetel proposed a zero direction queuing, which is not actually feasible due to like large size as well as the power distributions of the uh, data itself. And then there were other works focusing on Ethernet non-zero access, but it really doesn't focus on the workload imbalance of the graph data. And there have been implementation of in-memory techniques for graph processing, but it requires a lot of hardware overloads and then significant modifications. So that's another thing for that. So that's why this paper has been proposed. I will also talk about a little bit about the general requirements for this for understanding this paper. The first one is the graph convolutional network itself. So there will be three terms: A, X, and W. So A is for the adjacency matrix of the graph connections, and the edges. X is the input matrix, and W is the weighted matrix, right? So these two matrices need to be multiplied in the form of A times X times W. That gives the next input, but which then needs to be passed through a activation function, or generally a ReLU function, and then that will be the input matrix for the next layer of the graphs, right? So there's another thing called the power law graph. So before going into that, I'll just talk about the this value itself. So for the general density of the data set, so we're using 5 different data set for the paper: the Quora, CiteShare, PubMed, Nail, and Reddit. So for these different data sets, the adjacency matrix is very sparse. So only zero point 0.8 and all of these values. The weights are obviously dense at the first layer because they will be initialized, and then the input layer is also relatively sparse. So there will be a lot of zeros value in that. The X2 layer seems to be a little bit dense, but it's not that, because this now has to be passed through the activation functions, which actually makes it sparse again. So what the power law graphs tells is that a small number of rows or columns will have most of the non-zero values. So just these are the row IDs, and these are the number of non-zero values. So as you can see here, there will be some crest and there will be some troughs out here, whereas there will be some with the very high values, which are called so these are actually the uh, okay, sorry, the evil rows, right? So these high peaks are actually the evil rows, and then there will be other like crest and troughs, and there will be crest and troughs like that as well. So that's something that needs to be tackled. Okay, so for that, the first one is the baseline architecture for any graph convolutional network. So for that, a little bit of the background. So for the multiplication of A times X times W, there are two ways with this and this. So the second one would be preferred because it actually requires a lot less computation, because A itself is very sparse. So this is actually better. And the other one is we didn't necessarily need the matrix multiplication, but the for the sparse dense matrix multiplication, it uses a little bit different. So that's like column wise multiplication. So what happens is that a single column of the first matrix is multiplied to the column instead of the row, or instead of doing this times this, we are just doing column times column. So that will actually bring a partial result of that column multiplication. So this will multiply with this and give a partial result right here, and that will do again do the same for the other partial columns. After that, we move to the next one and then compute the other one, right? So what it does, it helps for the uh, obviously the parallelizing and the workload distribution. The other part is the use of the compressed sparse column CRC technique, and it kind of allows for that. The other one is directly mapping of the piece. So the data are mapped onto the P by rows. Like, so for example, for the four PEs here, so we just divide the 8 rows into the four significant rows, and then it's like multiply that. Obviously, there will be zero value and non-zero value inside that, but so we won't be talking that much into detail right here regarding the distribution. So this is the general architecture of the GCN baseline. So there are three parts here: the task distributor and queue, the PEs, and the accumulator and buffers. So I'll just talk about them in detail. So the task distributor and queue actually gives the various tasks and the workloads to the PE. There are actually two types of that. I'll just come back to that in a bit. The PE would have two units, the MAC and the AGU. So MAC is for the multiplication accumulation, and the AGU is for address generation unit. So that basically gives like where the data needs to be forwarded to later on, and these are for the accumulator and buffers of each PE. So the task distributor and queue actually does for the major part of the task distribution. So there are actually two parts of that: TDQ1 and TDQ2. So what these two difference is that this actually handles for those cases with the sparsity where sparsity is less than 75%, and this is for the higher than 75%, right? So for this each this is like the previous one. So the rows will be divided by number of rows, and they will be sent to each PE. So they're just divided by rows and then sent to OSP. There are additional unit right here, which are called stall buffers, raw checker, and arbiter. So what it basically does is that there is a hazard called as read after write hazard. So if such a hazard exists, then the other tasks will be queued in the stall buffer until the hazard kind of solves itself, and then only after that then the stall will be sent to the Ps. So that's like the protection system for that. In case of Ps with, sorry, in case of data with the high sparsity less than greater than 75%, so we'll be using CSV format. So for here, the data is in dense format, right? So all of the data is actually in the dense format, but when it's sparse, highly sparse, then we use CSV format for that, and we use a Omega network for distribution. So Omega network basically distributes this data onto different columns, and then then the Omega network is ended with the P's, right? So this is like for the two types of sparsity for the baseline. There's obviously change to that for the AWB, but this is for the baseline architecture. And then there are a few other modifications. The first one would be pipelining. So since like we're actually calculating several columns of data at a time, and we don't have to wait for the entire matrix to form for the next layer, because we're actually multiplying by the adjacency matrix, which is actually fixed for each of the layers, right? So since we can do that, we don't have to actually wait for the entire table. So whenever a graph is being processed and a part of the graph is being processed out of the parts of x times w, then we can multiply that part with a. So that's why we kind of can do this part in a pipeline, and we can even do that do multiple layers in pipeline like this. So this is like the entire execution of the P's in pipelining. The other part is for improving the bandwidth. There is something called matrix blocking optimization. So single agency matrix is divided into multiple groups in column wise. So for example, there will be four groups such as this, and then what we do is we take a single group of column or a single column from a group, and then we use that to multiply the data or intermediate value. So what happens is that since this is actually very small relative to the entire matrix, we can actually store this inside the on-chip memory, which boosts the total execution time. The other one is is the issue with the uh, with the like the utilization wave. So what happens is that for example, these are the several P's where each of the data is being distributed. So as you can see here for the nil data sets for certain rows, so this is the evil row, right? So for that there will be a huge utilization, and the other one will be idle for a lot of time, right? And that's the same for sites here as well. So they here utilization is very high, but the other P's have very low utilization. And not just this, right? For other cases as well, there are some small crests and troughs. So for example, this P has to work for a lot, while this P doesn't have to work for that much, right? So there will be some discrepancies here as well. So it kind of tries to balance out everything, including the wheel rows. So, okay, so for that, AWGCN has been proposed. So it uses two different phases. The first one is for distribution smoothing, and the second one uses remote switching and row remapping. So what it basically means is that if you just look at this figure right here, so these are the workloads at the bottom, or the row density of the matrix, and then in the top hand side, this chart right here is the execution of the parallel P's. So what happens is that, like for example, here there is a huge peak, so that a lot of time would be occupied for this execution for this specific piece, right? And this is like the evil row, so it has a lot of execution time as well, and there are time like that. So what the phase one does is it does two things. The first one is distribution smoothing. So what it does is that it kind of distributes the tasks to its immediate neighbors, right? So this will be distributed to this neighbor and this neighbor. That depends on the hops, right? You can distribute only one neighbor or the other two neighbors. That's like one hop and two hop. So with just this, it's kind of distributed to this one, right? So this will be distributed to here and here. So that's why this has been distributed here and this. So it's like kind of flattening the overall execution of the each the piece, right? So that's like the phase one, and in addition to that, they also count the number of jobs or tasks for each piece. So that's like a two thing, right? First, it's kind of smooth, as well as the counts the number of tasks. So the for the phase two, they uses both remote switching and row remapping. So since we already have the count of each PE, so for that it uses techniques to distribute all of these tags onto the entire PE array, so that it can be equally or evenly distributed among the PEs, right? So that's the second phase. So the evil row will be transferred to the PE with there will be specific PEs for that. For example, PE1, and then the other like local crest will be transferred to the global troughs or something like that. So basically, distributed smoothing does local balancing, whereas remote switching does global balancing. So for that, the what distribution smoothing does is that it's a part of in the TDQ1 and TDQ2. So for the first one with the low sparsity, so each task queue would be counting the number of tasks finished or the number of pending tasks, and then in the next round it just counts the which PE has the lowest pending tasks and then transfers that data into that PE, right? So for example, this could transfer here and here since the number of PEs could be less for this one, and then this can obviously do the processing for that will for the neighbor PEs only, and after processing it will just be sending that data back to the original PE. So that's like the original way for the TDQ1. For TDQ2, since we are using an omega network, we will be using at the last or the at the in layer of the omega network we'll have the distribution network, which kind of does the same thing as the TDQ1 and distributes the data based on the pending tasks of each PE, and the one with the lowest pending tasks will get the additional workloads. The other one is for the remote switching. For the remote switching, there will be something auto tuner right here. So what happens is that these are the tasks and distribution queue. These are the P's and these are the accumulation buffer, right? So there is a master P as well. We'll just talk about that in the evil row remapping. But for now, so each of the PE would have their own done status. So it will just report when they are done with their tasks. So that will be sent to an auto tuner, which is actually here. So that done status will be XORed with your previous done status to make sure that it kind of identifies the underloaded and the overloaded PEs. So that's done in the PE status monitor. It has three parts: PE status monitor, utilization gap tracker, and the workload distribution controller. So it tracks the unloaded and overloaded PEs and saves it into the switch candidate buffer. The arbiter makes sure that these PEs are not in their immediate neighbors because that is being controlled by the distribution smoothing part. So after that, it tells the utilization gap tracker to distribute those tasks based on the top underloaded and the top overloaded PEs. So after that, what the utilization gap tracker does is basically calculates the number of switches you drop using this equation. So if for the first iteration, I guess, so they were doing something equation like that, where GI is the workload gap and R is the number of rows per PE. And for the other one, to be doing that with the previous job switch as well, just to make sure it avoids the thrashing part. So to do all of this calculation, a separate circuit, a separate system has been built here. So the counter would be then left shifted G times and all of these things just to make sure that all of this calculation is done. So after this will then be reported to the third part, that is the workload distribution controller, which gets the number of utilization gap or the number of jobs to switch and then the corresponding IDs to switch, right? So then the PEs would then switch those tasks. So how it does that? It just change the data to a soft-link switch layer, which is before the PE switch for the PEs, and then they kind of shuffles the entire P data tasks between the P's, and then each P would be given if it's unloaded, it will take on a part of the overloaded tasks and so on and so forth. So that's how remote switching is done. The other part is evil row remapping. So for this, it's a special case. So what happens is that uh, whenever there is a very highly overloaded P that will be sent to the master P or the super P, it does one thing. It kind of calculates the number of non-zeros in the evil row, and then in the second phase, it distributes those evil rows into number of labor Ps. right? So for example, in this case, we have one, two, three, and four level PEs here. So it distributes inside into the four level PEs, which kind of accumulates at the end, right? And just to make sure the level PE doesn't get overloaded, their initial tasks would be switched using remote switching to some other PEs, and that's how they handle the evil row as well. So for the experimentation, they use this kind of setup. I will be talking that much in detail about this. And for the evaluation, they used the five data sets, and these five data sets, and then they define five different designs. The first one is baseline. So so all of these are for 1K PE. So for the baseline, there is no rebalancing. For the design A and B, so they are for with only distribution smoothing, but design A is for one hop and design two is for B is for two hop. For C and D, it's a one hop and B two hop, but with the addition of remote switching and row remapping. So design D, I guess, is the highest design with the two hop distribution smoothing and the remote switching and row remapping. So especially for this nail data graph, it uses two and three instead of one and two. So this is actually the result. So for the overall performance, okay, so yeah. So for the overall performance, it's actually seen that the for the layer one and the layer two, as we increase the design, right, it's kind of balances out, and then obviously the utilization of the hardware increases, and it kind of peaks at the for the design D, because that has the two hop and the row remapping, as well as the uh, remote switching. Yeah. So it's the same thing for each of the data set. It kind of increases. So there are some obviously some high peaks for nail, which has a lot of sparsity. For Reddit, it's not that increasing with the designs, because it has the lower sparsity regarding in respect to the others. And in detail, so, so the per SPMM performance, so for let's say for the only X times W utilization, and the X A times X W utilization, for the layer one, that's for the layer two as well. So as you can see here, it's actually smooths out here as well. And then the utilization is also, a number of operation cycles also increased right here, and it kind of balances out at the point for each of those graphs. And then sorry, the utilization actually balance out. The other part is for the okay. So for the hardware resource consumption, so for each of the data set, the hardware resource consumption is pretty high for each of the those, and then obviously the highest would be taken by the max, and the part will be from omega switching, and then task queuing, and then remote switching and row remapping would be minimum, because there will be not take that much hardware resources. In case of memory or on-chip storage, the remote switching and row remapping actually take a lot of storage, but still, compared to the baseline, it's comparatively lower. And the overall memory utilization or the on-chip demand is actually lower for the other designs. Okay, so uh, for the average utilization per round, or for the auto tuning, so what happens is, like, as the iteration increases, the auto tuner actually cancels out, or the saturates at one point. So first is for the distribution, as well as the row remapping, and the uh, sorry, and the remote swapping, right? So all of those cases actually does that, and at around the 10th iteration, I guess, for each of those data set, it kind of gets the highest or the most optimized balanced network. In case of scalability, as we increase the number of Ps from 512 to 1024, and then so on and so forth, for the baseline, the speed up actually drops a lot, even for design B, but for design D, it's almost the same. So sorry, the utilization, sorry, not the speed up, right? The utilization actually drops, but for the design D, the utilization doesn't drop. One of the expression is this one, where it doesn't really drop, and that's the reason. The reason for that is because there is not that much space to drop, right? So that's why it's being slow. But for each of those cases, the utilization is still the highest, although we scale it. And then the speed up obviously is the highest with the highest number of P's. So this is the comparison with the other baseline networks. So this is for with the CPUs, GPUs, SCNN, and then baseline Intel, right? So even for all of this, the AWB actually goes 1,000 times faster, 913 times faster, and all of those optimization in terms of speed, and then in terms of energy efficiency, it's actually highly efficient with on average, right? So compared to other prior GCNs and the prior accelerators, it's still a lot higher compared to the base GCN networks, and it's actually has a average low energy other or higher energy efficiency. So so the key takeaways here would be AWB-GCN actually addresses the critical challenge for large-scale graphs like optimization of workload distribution, and then the P utilization overall performance also improves with the this network. So